The universe is the ultimate mystery box. It's vast, it's ancient, it's filled with more questions than we have answers for. Every time we think we've got a handle on how things work, we pull back a layer and find something even stranger underneath. It's a cosmic detective story. We, humanity, are the sleuths on the case. We look up at the night sky, and we can't help but wonder, what's out there? How did it all begin? Where is it all going? The story of the cosmos is our story, written in the language of starlight and gravity. For most of human history, we thought gravity was the undisputed king of the cosmos. It pulls things together. It makes stars and galaxies. We assumed gravity would put the brakes on the universe's expansion, which started with the Big Bang. Maybe the expansion would slow down enough to stop or even reverse. But the universe had a surprise waiting for us. Imagine you toss a ball into the air. Now imagine it doesn't slow down, it speeds up. Well, that's exactly what astronomers discovered was happening to our entire universe. So what exactly is dark energy? The simple answer is, we don't really know. But we can define it by what it does. Dark energy is the name we give to the unknown form of energy that appears to be causing the accelerated expansion of the universe. It's a repulsive force, a kind of pressure that pushes space itself apart. Think of it as the opposite of gravity. While gravity pulls matter together, clumping it into stars and planets and galaxies, dark energy pushes everything apart on the grandest scales. It's a cosmic tug-of-war. Right now, dark energy is winning, hands down. This isn't just some fringe idea, it's a cornerstone of our current best model, lambda CDM. The lambda part stands for the cosmological constant. The CDM stands for cold dark matter. Pie chart, 68% dark energy, 27% dark matter, 5% normal matter. All the stuff we can see, the stars, the galaxies, the planets, you and me, accounts for less than 5%. About 27% is dark matter. The rest, a whopping 68%, is dark energy. The universe is mostly made of something we can't see and don't understand. It's like exploring a new continent and realizing over 2/3 is shrouded in impenetrable fog. Dark energy dictates large-scale structure evolution and the ultimate fate of our entire cosmos. Understanding it is one of the most important goals in all of science today. It represents a fundamental challenge to our understanding of physics. To understand how dark energy affects the universe, let's go back to the Big Bang. About 13.8 billion years ago, the universe began in an incredibly hot, dense state and started expanding. For the first several billion years, this expansion was slowing down. Gravity was in charge. The collective gravitational pull of all the matter was acting like a cosmic brake. The galaxies were still moving apart, but the rate was decreasing. Then, about 5 or 6 billion years ago, the universe hit a tipping point. As the universe expanded, the density of matter decreased, but dark energy seems to have a constant density. It doesn't dilute. So the influence of gravity weakened while the repulsive push of dark energy remained constant. Eventually, dark energy overpowered gravity. The cosmic brakes failed, and someone slammed the accelerator. From that point on, the expansion began to speed up. It entered a new era of cosmic acceleration, the one we live in today. Every second, the space between distant galaxies stretches a little more than before. The farther away a galaxy is, the faster it appears to be receding. There's more space, and more dark energy, between us and that galaxy, pushing us apart. This has profound implications. If this acceleration continues, galaxies not bound to our local group will be pushed away until their light can no longer reach us. They will cross a cosmic event horizon. The night sky, in the far distant future, will look very different. Our descendants will see only the Milky Way and immediate neighbors, a seemingly empty, lonely universe. So how do we know all of this? This isn't just speculation. The case is built on multiple, independent lines of hard evidence. The first bombshell dropped in 1998. Two separate teams studied a particular kind of exploding star, type Ia supernovae. These supernovae are fantastic cosmic measuring sticks. We call them standard candles. They explode with nearly the same intrinsic brightness. Measure how dim they appear and you get their distance. The most distant ones were dimmer, therefore farther, than a decelerating universe predicted. Extraordinary claims require extraordinary evidence, and the supernova data doesn't stand alone. Galaxy mapping provides an independent line. Large 3D maps show filaments, voids in the cosmic web. Subtle wiggles and clustering are baryon acoustic oscillations, a standard ruler confirming supernova results. The cosmic microwave background, the oldest light, provides geometry and critical density constraints. Tiny fluctuations tell us the universe is close to flat, implying missing energy. Observed matter, baryonic plus dark, sums to roughly 32%. The missing roughly 68% must be something else, dark energy. The supernova discovery later led to the 2011 Nobel Prize in Physics. Supernova, BAO and the CMB form a consistent, independent tripod of evidence. Skepticism remains healthy, but the body of data is robust. Together, these observations reveal an accelerating cosmos governed by an unknown energy permeating space. Okay, the evidence is solid, but what is dark energy? Here's where observation becomes theory, and the ideas get wild. The leading suspect, Einstein's cosmological constant. Einstein added a constant term to GR to allow a static universe, later called his biggest blunder. Lambda represents the energy of empty space, vacuum energy. Quantum fields make empty space fizz with virtual particles, which could supply vacuum energy. But when physicists calculate this vacuum energy, they get a number outrageously too large, about 10 to the power of 120 times larger, the cosmological constant problem. It's one of the biggest embarrassments in theoretical physics. An alternative, quintessence, a dynamic scalar field that can change in time and space. Unlike a constant, quintessence is flexible and may evolve. Its strength could change, producing observational differences over cosmic time. Some propose our understanding of gravity is incomplete. Maybe GR breaks down on the largest scales. Modified gravity theories try to explain acceleration without dark energy. For now, the main contenders, cosmological constant, quintessence, modified gravity. Each idea raises new questions. What produces the field? Why this value? They invite creative, exotic physics and healthy skepticism. We need more data. New telescopes and surveys will test these theories with precision. It's easy to get dark energy and dark matter confused. Dark energy, dark matter. They both have dark in their names and huge mystery, but that's where it ends. They are two completely different things with opposite effects. Think of them as two cosmic rivals. Dark matter is clumpy, dark energy is smooth and uniform. Dark matter is the architect that builds structures. Dark energy is the force trying to blow the building apart. Dark matter has mass and gravity. It clumps and forms halos around galaxies. We infer it from gravitational effects like rotation curves and lensing. Dark energy is a form of energy, not matter, causing repulsion. Here's an analogy. Imagine baking raisin bread. The dough is space-time, the raisins are galaxies. Dark matter is like invisible sticky bits that make raisins clump. Dark energy is the yeast, but a super yeast that makes the dough rise faster and faster. So while dark matter holds things together, dark energy pulls them apart. In short, dark matter attracts, dark energy repels. Both shape our universe in very different ways. The discovery of dark energy opened a new frontier in physics. It's a giant flashing sign. Our theories are incomplete. We are standing at the edge of a vast ocean of ignorance. Scientists are designing powerful new instruments to attack the problem. It means profound discoveries that could revolutionize our understanding of space, time, and energy. We are entering a golden age of cosmology. Ground surveys like the Vera C. Rubin Observatory will map billions of galaxies. Space missions like the Nancy Grace Roman Space Telescope will survey deep fields. Euclid will measure shapes and distances with exquisite precision. They will measure positions, shapes, and distances of billions of galaxies. Weak lensing will reveal dark matter distribution. Supernova surveys probe expansion history. By building a detailed expansion history, we can test if dark energy is constant or changing. This will help distinguish a cosmological constant from quintessence or modified gravity. These experiments will test theories with incredible precision. If it's a constant, we must explain why vacuum energy is so small, a profound theoretical challenge. It could require a deeper theory unifying quantum mechanics and gravity. If instead we find dynamics, it points to a new field, perhaps a fifth force. Either way, it would be monumental. You might be thinking, why should I care? It's about distant galaxies and abstract theories. True on the surface. But its importance runs much deeper. It's about our place in the cosmos. Understanding fundamental laws governs existence. Where we came from and where we're going. It touches the ultimate fate of everything we know. While it won't cure a disease tomorrow, the pursuit drives technology. Astronomical CCD development helped lead to digital cameras in our phones. Big data techniques from sky surveys push advances in medicine, finance, and AI. This quest is part of what makes us human. Understanding dark energy is the next great step in cosmic discovery. You can't claim to understand the world if you don't understand 68% of it. Fundamental science drives unexpected innovations. Most importantly, it gives perspective. A humble reminder of our smallness and wonder. It connects us to a 13.8 billion-year story of cosmic evolution. In a divided world, the shared quest to understand the universe can be unifying. Understanding dark energy is the next chapter in a grand human story. It's a matter of curiosity, perspective, and the technologies that follow, all reasons to care. The nature of dark energy will determine the final act of our universe's story. It holds the key to our cosmic destiny. If dark energy is a cosmological constant, the future is perpetual accelerating expansion. The universe will become increasingly cold, dark, and empty. Galaxies will become isolated islands in an endless dark sea. This scenario is called the Big Freeze or heat death. If dark energy is dynamic and decreases over time, gravity could regain control. The expansion could halt and reverse. A big crunch, possibly leading to a new Big Bang in a cyclical universe. If dark energy strengthens with time, we face the Big Rip. Clusters, galaxies, solar systems, even atoms could be torn apart. The fabric of space-time itself would be torn asunder. Which fate awaits our universe? The answer is hidden in the nature of dark energy. By studying it, we are not just solving a puzzle. We are reading the final chapter. We are part of this story, and the desire to know how it ends is deeply human. We are the generation of explorers who have just begun to read it. Keep looking up. Thank you for joining this cosmic investigation. See the description for sources and next steps to keep learning.